Welcome to Chapter 3. This should be a single lecture. It's a short chapter. We're going to introduce a few things about organic molecules, introduce functional groups, and so let's get to it. Chapter 3 is, again, organic molecules and functional groups. And what I want you to do is start by memorizing the functional groups. FG you'll see for functional groups. If you look inside cover, the very first page, common functional groups. Within those, there's more common and less common, but those are the functional groups, and we'll talk about several of them. And so memorize them. Start making flashcards or whatever. And I want you to understand the reactivity of functional groups. Okay, we're going to learn that as we go, but you're going to understand how these direct the molecule to do things. Functional group is the direction of the molecule. It is an atom or a group of atoms with characteristics. It's the reactive part of the molecule. Okay? So, as opposed to CC bonds and CH sigma bonds, okay, certainly CH alkane bonds, these bonds are not easily broken. Okay. However, heteroatoms and multiple bonds are more easily broken. Okay, so there's heteroatoms like nitrogen, oxygen, fluorine, chlorine, bromine, iodine, sulfur, etc. And there's multiple bonds, pi bonds. So let's look at an example of each. We talked about this in chapter 1. Here's this carbon-oxygen bond. You have a dipole. Because of the more electronegative oxygen, you have a dipole. You have a partial plus on carbon and a partial minus on oxygen. The carbon, we would label this as electron deficient. It's very important. Dipoles are very important. Okay. Now, if you look at a multiple bond, a carbon-carbon double bond, for example, we've sort of hinted at this already. These pi bonds are easier to break, and they can attack things, leaving behind a carbocation. Okay. So 3.1 is just sort of an intro to these functional groups. And then 3.2 is sort of an overview. Okay, you'll see sort of R, F, G. Okay, R is some generic carbon skeleton. FG is functional group. Functional group can be an alcohol, an amine, a bromide, etc. Okay, so 3.2 is there's functional groups here, organic functional groups. Within that, you have hydrocarbons. That means molecules with only hydrogen and carbon. Within that, you have aromatic, which we will touch on in organic 1, but not a lot about. And then you have aliphatic, which we'll spend a lot more time on. Within aliphatic, you have alkanes. That's the next chapter. You have alkenes, that's double bonds. And you have alkynes, triple bonds. So that's hydrocarbons. That's a large quantity of these. CZ bonds could be alkyl halides, ALKIL, alkyl halides, alcohols, a COH, a thiol is the sulfur version of that, ethers, amines, etc. Okay, so it's a carbon something single bond. And then you have basically CZ double bonds. We're really focused on CO double bonds. You can have CN double bonds, but there's a lot of them. Aldehyde, ketone, carboxylic acid, ester, amide, acid chloride. We'll get to most of those, really. We'll see those in organic 2. And we'll see some of these here in organic 1 coming up after we do hydrocarbons. That's sort of an outline. So let's look at 3.2a. Okay, alkanes. We've seen a couple of these already. An example is ethane. We really don't need to go through all these, but it's fine. Alkenes would be ethene by the naming, but it's ethylene is the common name. Carbon-carbon double bond. We did these when we did hybridization. Alkynes are a triple bond. And ethyne would be the IUPAC name, but we call this acetylene. And then aromatic looks like alternating double bonds, but it's actually more complicated than that. If you put 3 double bonds in a ring, this is actually benzene, and this has a resonance form that is degenerate or equal in energy. So these aromatic molecules have special properties. Okay, a hybrid would look something like this. Okay. Those electrons are shared perfectly. So that's 3.2a. 3.2b is the second category where you have a Z. So Z is more electronegative than carbon. Carbon is electron deficient. Partial positive, partial negative. Alcohol, ROH, lone pairs. I'll put the lone pairs on the first one, and then you can fill in. So you could have methanol if R is a CH3, or ethanol if it's CH3CH2. You have thiols, that's SH, there's 2 lone pairs on sulfur. Ether, ethers and alcohols are similar, but different. ROR, sulfide is the sulfur version of ether. And then you have RX. X can be fluorine, chlorine, bromine, or iodine. These are alkyl halides. So CH3 will be methyl chloride or methyl bromide, chloromethane. Okay? And then finally, you have NH2. And you can have other R groups on the nitrogen. You can have 3 alkyl groups. There's lots of different amines. Okay, so these were alkyl halides up here. We're just reviewing these to help you learn them. Finally, 3.2c is carbonyl chemistry. Partial plus. You still have a dipole here, but now you have a dipole with a double bond. Okay, there's a lot more that goes into this. Aldehydes. One of these groups is an H. Ketones, there's no H. R and R prime, let's say, 2 different R groups. They could be the same. Ketones. Could be symmetrical, they can be unsymmetrical. And then you have carboxylic acids. Like acetic acid, if R is a CH3, this H is acidic. It's the most acidic organic functional group there really is, except for sulfonic acid, which we touched on at the end of chapter 2. Okay, that makes it unique. And then all the other ones are based on this. So there's acid chloride. These are carboxylic acid derivatives. There's something called an anhydride. There's esters, there's thioesters, there's amides with nitrogen, right? You can have R groups there or H's, doesn't matter. And then there's a nitrile, and that's a little bit different. It's a carbon-nitrogen triple bond. So that's functional groups. Just memorize those. 3.3 is intermolecular forces. Right. It's actually a very, very important concept because it's important to remember that, I'm trying to say, that all molecules, they have bulk properties. That's based on intermolecular forces. The bulk properties impact how things behave. So keep that in mind when you're looking at a piece of paper and you have 2 molecules that you're looking at, or two written formulas. Those represent bulk formulas, bulk properties of organic molecules. Okay, these are forces that exist between molecules. Okay, like international forces will be international forces between nations. Okay, forces that exist between molecules. The functional group drives this. Okay, so let's first look at the ionic. There's actually 4 intermolecular forces. we're really going to focus on 3. But ionic, you're familiar with. This is a very strong electrostatic interaction. So we've seen this before. Na plus, Cl minus. We talked about electron transfer or sodium fluoride or whatever. Electron transfer from sodium to chloride, and then you have this Na plus Cl minus. There's plenty of these kinds of compounds. And we'll see some of these, but they're not our focus. These are the strongest of these 4 forces. Strongest intermolecular force. Okay. Electrostatics are a very strong force. But if we look at the 3 covalent, this is what we really want to understand more about, we want to focus on. We have van der Waals or London dispersion forces. This is a momentary change of electron density. It's a dipole, but it's temporary. Temporary dipole. So another way to think about it. Temporary dipoles. Whereas dipole-dipole interactions are permanent dipoles. That's all we mean. So really, you could break the first 2 down into temporary dipoles and permanent dipoles. So dipole-dipole interactions are just attraction or interaction of permanent dipoles. So a carbon-oxygen bond, for example, is permanent. A carbon-carbon bond or a carbon-hydrogen bond, things can fluctuate or polarize. Okay, you can get a partial positive and partial negative temporarily. Finally, we have hydrogen bonding. Hydrogen bonding is the strongest of the 3 covalent intermolecular forces. This is a hydrogen atom attracted to a heteroatom. Hydrogen atom attracted to an oxygen or a nitrogen, basically. Okay, it's an attraction between H of one molecule and O or N of another. Okay, so you should write these down and more clearly work through these. I'm not going to ask you for these definitions. I want you to understand the implications. So the strength is the strength is increasing down here, and this is the strongest. Okay, so if I asked you to put them in order, maybe I could ask something like that. And I could include the ionic. The ionic's the strongest, then hydrogen bonding, then dipole-dipole, then van der Waals. So let's talk about each one of these 3. Van der Waals. All organic molecules possess VDW van der Waals forces. Alkanes possess van der Waals forces only. Okay, that's all they got. CH bonds. Bending and stretching of bonds creates a temporary dipole. So I want you to remember that larger surface area, stronger van der Waals. Okay, more CH bonds over a greater area, stronger van der Waals. Again, the stretching and the bending of these bonds creates this temporary dipole. Larger surface area equals stronger van der Waals. So pentane, skeletal structures. We'll get into these types of structures. That's a CH3, it's a CH2 there, CH2, CH2, CH3. You'll see this very soon. Neopentane is 3 CH3s. These wedges and dashes, we'll get into what that means. Okay, you got 4 CH3s around a central carbon. There's a carbon there. Okay, this is called neopentane. Okay. Not a name here. There is less surface area in neopentane. Okay. All right, so larger atom size, stronger van der Waals forces. So, polarizability, back to that kind of chapter 2 acid thing. I2 is going to have stronger van der Waals because of larger atom size. Okay, van der Waals are just not that, they're not all that exciting. Dipole-dipole interactions. Alkanes do not possess these forces. Let's look at an example of a carbonyl. Okay. This is acetone. It's going to have an interaction because this is partial minus. The carbon has a partial plus, right? Partial plus. And you can imagine just this endless string of oxygens interacting or lining up with the partial positive carbon of another molecule. It's not a bond, it's sort of a net attraction. Okay, and this oxygen could do the same thing here, etc. Okay, so on and so on. So then hydrogen bonding is the third, and it's typically a hydrogen bonded to a heteroatom, mainly oxygen and nitrogen. That's what we're talking about. Oxygen is even more common. Okay, it's an electrostatic attraction, so think of sodium plus and O minus or something like that. HO minus, sodium hydroxide. Well, now you have an H plus or a partial positive on an H. It's not an H plus. It's the lone pairs on an oxygen are going to be electrostatically attracted to the hydrogen on another molecule of water, for example. So an H has a partial plus and an oxygen partial minus, partial plus. This partial minus is interacting with the partial plus. So it is electrostatic, like ionic, but it's not as powerful. Okay? Any oxygen with a hydrogen atom, and so you're talking about a hydrogen bonded to a heteroatom and then interacting with another heteroatom. All right. So carboxylic acids, alcohols, amines, those kinds of functional groups can do hydrogen bonding. Let's look at 3.4. This is physical properties. Okay. We're going to see how these intermolecular forces impact these physical properties. So let's look at 3 physical properties. Boiling point, melting point, and solubility. Boiling point is the temperature at which a liquid becomes a gas. There's a certain energy requirement for that. Stronger intermolecular forces equals higher boiling point. Stronger intermolecular forces, higher boiling point. So that means van der Waals. Things that only have van der Waals are going to have lower boiling points than things that only have dipole, and lower than hydrogen bond. And that makes sense that ionic compounds are going to have even higher boiling points. You see a lot of solids, sodium chloride, and things like that. So, stronger intermolecular forces, more surface area. More surface area, higher boiling point. Okay. And finally, more polarizable atoms, higher boiling point. Okay. Let's look at melting point. Similar trends. Melting point. Temperature at which a solid turns into a liquid. There's an energy requirement for that. Stronger intermolecular forces. I'm just going to say IMFs. Stronger intermolecular forces. What does that mean? Higher melting point. Again, those intermolecular forces are stronger. They're holding things together. Okay? Now, the deviation from the surface area is still true with melting point. Okay. Yet there's an exception to this. It's more about symmetry. Okay? So higher symmetry, higher melting point. This makes sense because the more symmetrical something, the more crystal packing goes on. Okay? It's all about sort of crystal packing. And finally, the third one is solubility. And what I want you to just remember is like dissolves like. similar intermolecular forces will interact. Similar intermolecular forces will interact more readily. Okay, so things with hydrogen bonding are going to dissolve things that can hydrogen bond. Okay, it makes sense. Alkanes are going to dissolve alkanes. Okay, so 3.5 through 3.7 are all very interesting. It's vitamin A, soap is 3.6, and the cell membrane, very interesting cell membrane. You should look through those. Okay, you should read through these sections. I'm assigning them to look through. They'll be covered in Learn Smart. You should learn something about these. These are practical applications. They're phenomenal. Okay, what I'm going to focus on in the lectures is our more conceptual, organic, arrow pushing types of things. All right. Again, 3.9 is biomolecules. Very interesting. DNA. Lots and lots of interesting stuff. Let's look at 3.8 to finish up here. 3.8 is functional groups and reactivity. Like I said, a functional group creates a reactive site. We said this in the acid-base chapter. The first handout I give you in class is acids, bases, electron-rich, electron-poor, electrophile, nucleophile, Lewis base, Lewis acid, etc. These terms matter. Okay, so electron-rich will attack electron-poor. Nucleophiles will attack electrophiles. Lewis bases, Lewis acids. Bronsted bases, Bronsted acids. Okay. Electronegative atoms, N or O or X, sulfur is included in that. What do? They create a dipole, create an electron-deficient carbon or hydrogen. Okay, HX is a great acid. HCl is a great acid. Okay, C, carbon Cl bonds are good dipoles. Okay, so what do we mean by that? Let's look at an example. CH3. You'll learn about how to draw these things out in chapter 4. What do we have? We have a dipole, right? Just like HCl makes an acidic proton, this makes an electron-deficient carbon. It's partial positive now. A nucleophile can come in here and attack. We're going to talk a lot more about what we mean by that. Okay. So lone pairs. Okay. So there's dipoles, and then there's lone pairs, which are part of the atom that creates a dipole. But for nitrogen and oxygen especially, those lone pairs can do different things, i.e. hydrogen bond. X is different. X not as much. Okay, and that's because there are these electronegative atoms. Those lone pairs are held closer in a sense. Fluorine, chlorine, bromine, iodine, those lone pairs are held more tightly because of the the seventh column that they're in. They really want to keep their electrons, even more so than nitrogen and oxygen. So these lone pairs create nucleophiles or bases. What do I mean by that? You have an oxygen with a lone pair, much more so than fluorine, chlorine, bromine, or iodine. These lone pairs can reach out and interact with things. Okay, amines are better bases than ethers. Okay, and that has to do with the electronegative effect or the element effect. Better bases. Okay, better base meaning it's more prone to go and attack. Again, oxygen electrons are held even closer than nitrogen, so it's a trend. It's the element effect. It's the first major effect we talked about in chapter 2. Finally, we have pi bonds. This is carbon-carbon, or it could be carbon-oxygen double bonds. These create nucleophilic sites because they're more easily broken than sigma bonds. Because of the nature of the pi bond, more easily broken than sigma bonds, they create nucleophilic sites. We've been showing this. I'm going to keep showing it. We'll get to this in Organic 1. This is going to reach out and pick up something, an electrophile, an H+, or something else. And so that reaches out. It's a nucleophile. It's just not a lone pair. It's going to reach out and attack and form a carbon-hydrogen bond, for example, and leave behind a carbocation at that position. Okay, we'll get into that in chapters 10 and 11. All right. So again, electron-deficient carbon can react with a nucleophile. Electron-rich carbon can react with electrophiles. Okay. So let's show examples of both of those. electron-rich carbon. I'm sorry, scratch that. Electron-deficient carbon, okay, that's category 1 or whatever, is, we're showing this in lots of different ways, okay? CH3Br, dipole, electron deficient, partial positive. Those react with nucleophiles. You got a nucleophile with a lone pair. It's going to come in here, and what it's going to do is attack that carbon. It's attacking the carbon, not the bond, pushing out the bromine. Okay, we'll be much more precise in our arrows coming up. Okay, so that forms a nucleophile carbon bond. This is going to be called SN2. We'll get to that. Okay, but we formed a new bond. We broke a carbon-bromine bond. Bromine is leaving. We'll get to all that. And then electron-rich carbons can react with electrophiles. Electron-rich carbons, such as alkenes. I've been showing this several times now. Alkenes can react with some sort of electrophile. It could be a proton. It could be something else. We'll see a lot of this in chapter 10. And you generate a carbocation. You generate some sort of carbon E bond, CH bond, lots of other things. Okay, there's many, many others. And we'll leave it at that. Okay, this is just an intro to functional groups. What I'll say about 3.9 is fascinating is that functional groups dictate life. Okay, biomolecules are everywhere and they depend on functional groups. Okay, so functional groups have a lot to say about the molecules that make up living things. So that's pretty interesting section. But with that, we'll wrap up chapter 3, and we'll come back and do chapter 4 next.